The Kepler 4.5b mission was humanity's boldest leap toward the stars. Launched in 2032, the probe was designed to study the exoplanet dubbed Earth's cousin, a rocky world orbiting a sun-like star 1,400 light-years away. For years, it beamed back data spectroscopic readings, atmospheric compositions, and faint glimpses of a distant surface that teased the possibility of liquid water. By 2041, when its solar panels began to fail, Kepler 4.5b sent its final transmission, a dense packet of raw telemetry data, catalogued and shelved by NASA as a routine. No fanfare, no breakthroughs, just another quiet chapter in the search for habitable worlds, or so we thought. Decades later, in 2055, a new breed of artificial intelligence emerged, one not bound by the limits of human pattern recognition. This neural network, developed for decoding cosmic background radiation, was trained to sift through petabytes of archived space data, hunting for anomalies no scientist had ever considered. Graduate student, on a whim, fed Kepler 452b's final transmission into the system. The AI didn't just process the data, it froze mid-analysis, its quantum processors spiking as if encountering something incomprehensible. When the output finally came, it wasn't a report, it was a map. The map pointed to a specific frequency buried in the telemetry, a signal so faint it had been dismissed as noise during the original mission. But this wasn't noise. The AI isolated a repeating pulse, a sequence of oscillations, that didn't match any known stellar or atmospheric phenomenon. When visualized, the signal formed a geometric lattice, a three-dimensional structure that seemed to shift depending on how it was viewed. Like an optical illusion etched into the fabric of space, researchers stared at their screens, their coffee growing cold. This wasn't a glitch, it was deliberate. The signal's origin wasn't Kepler 452b's surface but a point in its upper atmosphere, where charged particles danced in a magnetic field eerily similar to Earth's auroras. The AI cross-referenced the pattern with every known dataset, from Voyager's radio bursts to the Arecibo message we sent into the void in 1974. Nothing matched perfectly, but there was a chilling similarity to a signal captured once before, in 2039, by a radio telescope in Chile. That signal, dubbed the Andes Whisper, had been written off as interference. Now, the AI suggested otherwise. The two signals shared a mathematical rhythm, a cadence that hinted at intent. What made the discovery unsettling wasn't just the signal itself, but its context. Kepler 452b's atmosphere, according to the probe's data, was thin but dynamic, with storms of ionized particles swirling in patterns that defied chaotic weather models. The AI flagged these storms as non-random, their movements aligning with the signal's pulses as if the atmosphere itself was a canvas for something larger. When researchers plotted the data over time, they saw it. The pulses weren't static. They evolved, growing more complex the closer Kepler 452b's orbit brought it to the planet's magnetic poles. The team hesitated to publish. This wasn't the kind of finding you announce without triple-checking. They ran the AI through every possible error check, recalibrating its algorithms to rule out artifacts or coding biases. Each time the result was the same. The signal was real, and it was structured. One physicist, a veteran of exoplanet studies, described it as like finding a symphony in a storm. Another, more skeptical, called it a statistical fluke we can't explain yet. But the AI offered a third perspective. It didn't just detect the signal, it began predicting its next iterations, as if the sequence was still unfolding across light years. The implications were dizzying. If this was a signal, who or what had sent it? Kepler 452b was too far for any human probe to have planted it, and no known natural process could produce such a precise, evolving pattern. The team dug deeper, feeding the AI more of Kepler 4.5b's archived data. That's when they found the second anomaly. Buried in the probe's ultraviolet imaging was a faint glow in the planet's atmosphere, a shimmering lattice that appeared only in specific wavelengths. To the human eye, it was invisible. To the AI, it was a blueprint. This lattice wasn't just light. It was a network of charged particles, arranged in a grid so intricate it resembled circuitry. The AI calculated that the grid structure was mathematically consistent with the signal's frequency, as if the two were parts of the same system. When the team converted the lattice's geometry into a digital model, it mirrored patterns found in quantum computing, patterns we'd only begun to explore on Earth. The idea was unthinkable, yet unavoidable. This wasn't just a signal, it was infrastructure. The discovery sent ripples through the scientific community. Quietly, a task force was assembled, pulling experts from astrophysics, cryptography, and theoretical physics. They worked in a secure lab, their findings embargoed even from their colleagues. The AI, now running 24/7, began to uncover more. It found echoes of the same lattice in Kepler 4.5b's magnetic field data, suggesting the planet's entire magnetosphere might be part of the system. The signal's pulses, it turned out, weren't random bursts but a modulated stream, like a broadcast that had been active for centuries, waiting for something to hear it. One question haunted the team. Why Kepler 4.5b? The planet was a prime candidate for habitability, with a stable orbit and signs of water vapor. But it was no closer to Earth than thousands of other exoplanets. Why would a signal, potentially a message, be embedded in its atmosphere, hidden in storms and magnetic fields? A cryptographer suggested it might not be a message at all, but a marker, a beacon left by something that had long since moved on. Another theorized it was active, responsive, perhaps even aware of the probe's presence. To test this, the team reanalyzed Kepler-452b's final orbits. The probe had been programmed to adjust its trajectory based on atmospheric data, dipping closer to the planet's poles in its last months. The AI revealed something chilling. The signal's complexity increased with each pass, as if it was reacting to the probe's approach. The lattice in the atmosphere grew sharper, its pulses more frequent. It wasn't just broadcasting, it was adapting. The task force debated what this meant. A natural phenomenon adapting to a probe's orbit was unheard of. A deliberate one was terrifying. They turned to the AI for answers, tasking it with simulating the signal's behavior over time. The results were staggering. The signal wasn't just evolving, it was optimizing, refining itself as if preparing for something. The AI projected that, had Kepler-452b's mission continued, the signal might have reached a threshold, a point where its structure became fully coherent, like a completed circuit. The team's lead scientist, a woman who'd spent her career chasing exoplanet signals, couldn't sleep. She kept returning to the AI's visualizations, watching the lattice pulse in sync with the planet's storms. It felt alive, she admitted in a private log, though she hated the word. Not alive in a biological sense, but purposeful, like a machine left running in the dark. She began to wonder if Kepler-452b wasn't just a planet but a node, part of a network spanning light years. It was invisible until we've built something smart enough to see it. The task force faced a dilemma. Publishing would spark global debate, but it could also invite panic or misinterpretation. The signal wasn't a friendly hello or a clear warning, it was too alien, too ambiguous, yet keeping it secret felt like a betrayal of science. They compromised, releasing a sanitized paper on anomalous atmospheric patterns in Kepler-452b's data, burying the signal's implications in technical jargon. The public barely noticed, but a few amateur astronomers and conspiracy theorists picked up the thread, their forums buzzing with speculation about alien tech and cosmic cover-ups. Meanwhile, the AI kept working. It began cross-referencing the Kepler signal with other datasets, from distant pulsars to the cosmic microwave background. It found faint echoes of the same lattice in places no one had thought to look: distant galaxies, ancient light, even Earth's own ionosphere. The patterns were subtle, almost ghostly, but they were there. The team realized they weren't just studying a signal from Kepler-452b, they were uncovering a framework, a structure woven into the universe itself, hidden until an artificial mind stumbled across it. Now, the questions multiply. If this is a network, who built it? Why hide it in the chaos of a planet's atmosphere, in the flicker of distant stars? Is it dormant, or is it watching? The Kepler-452b probe is long gone, its circuits fried in the void. But its data lives on, whispering truths we're only beginning to hear. The AI unrelenting churns through more archives, finding new traces of the lattice in places we never imagined. Each discovery pushes us closer to an answer or further into the unknown.